So, in the previous lecture we were looking at the unsteady heat conduction from a spherical particle. Okay. So, the problem was that you had a spherical particle at temperature T1 initially, okay, at temperature T1 initially, which was dropped into a fluid with temperature T0. Okay. An initial particle with temperature T1 initially was dropped into a fluid with temperature T0, radius of the particle was r, and we had assumed that the thermal diffusivity of this particle is alpha. So, the boundary conditions are that at the surface T is equal to T0 because it is in contact with the fluid, and we had assumed there is no heat transfer resistance in the fluid. At initial time T is equal to T1 throughout, okay, and we wanted to find out how the temperature evolves with time as time progresses. We have defined scaled variables so that the temperature at the surface is equal to 0 and the initial temperature is 1, and the surface is at r star is equal to 1. And then the boundary conditions were that at r star is equal to 1, T star is equal to 0. At there was a symmetry condition at the center from the requirement that the derivative has to be uniquely specified at the center. If you recall, we had drawn an analogy with the boundary condition at the axis of a cylinder where there is no physical boundary at the cylinder, and just the requirement that the derivative has to be uniquely specified independent of the direction from which the axis is approached. The derivative has to be uniquely specified. That condition resulted in a condition that the derivative has to decrease to 0 at the origin, okay, in this coordinate system, and at initial time T star is equal to 1. So, this was the scaled equation where we had scaled the time by the diffusion time r square by alpha, okay, and if we do that we get an equation and boundary and initial conditions that are independent of any parameters. Okay. The steady solution in this case is identically 0, okay, because in scaled coordinates the temperature is the same T0 everywhere in the long time limit, and therefore, the steady solution is Ts is equal to 0. Okay. We had used separation of variables, okay, to get a solution for the equation. Okay. Substitute f of r times g of t into the equations, divide throughout by f times g, then one side is only a function of time, the other side is only a function of r, both have to be constants. That constant has to be negative so that the temporal part decreases exponentially as time progresses, and then you get this equation for the function f of r. Okay. And you can show that this function actually satisfies this equation here. Okay. So, I will just go through that. Okay. So, let me write. That means that df by dr is equal to, differentiate using chain rule, first the numerator and then the denominator. Okay. So, a beta cos of beta r by r, okay, minus a sine of beta r by r square, okay, plus, okay. First the numerator, you will get here, you will get for the numerator it will be a negative sign because derivative of cos is minus sign. Okay. So, I get minus b beta sine of and then differentiate the denominator minus b cos of beta r star by r star square. The second derivative d square f by dr square. Okay. first differentiate the numerator. Okay. I will get minus a beta square sine of beta r by r, okay, and then differentiate the denominator. So, I will get here minus a beta cos by r star square. That was from the first term here. Okay, that was from the first term here. Okay. The derivative of the second term, the numerator, will give you a contribution that is identical to this. Okay. The differentiate of the numerator from the second term will give you a contribution identical to this. So, I will get 2 times here. Okay. And then I have to differentiate the denominator. Okay. I have to differentiate the denominator, and I will get here plus, okay, 2 a sine of beta r by r cubed. Okay. Derivative of 1 over r square is minus 2 by r cubed. Okay. So, that is the first term. Okay. Now, I have to differentiate the second term here, okay, and I use the same procedure. So, I will get minus b beta square okay. So, I have to differentiate the first term here, and minus b beta square cos of beta r by r star. Okay. Then I differentiate the denominator, and I will get plus, okay, 2 b beta sine of beta r star by r star square. Okay. Actually, if I differentiate the denominator in this term here, I will get this one. If I differentiate the numerator here, I will get the same value. So, I get 2 times that. Okay. And then I have to differentiate the denominator here. Okay. And if I differentiate the denominator, I will get plus 2 b cos of beta r by r cubed. Okay. Please note that it should be r cubed here, because if you differentiate 1 over r square, I get 1 over r cubed. Okay. So, in this equation, I have d square by dr square plus 2 by r times d by dr. Okay. Okay. So, I have to add 2 by r times this. Okay. So, if I put in a factor of 2 by r here, okay, this whole thing gets multiplied by 2 by r. Okay. And now you can see that these terms will cancel out. If I multiply by 2 by r, okay, this will cancel out with this one with this one, okay, this one with this one, and this last term will get cancelled out with this one, leaving me with just in the end minus beta square into a sine of beta r by r plus b cos of, okay, which is minus beta square f. Okay. So, just to show you that this solution actually satisfies the equation. Okay. It satisfies the differential equation that I had earlier. Okay. Okay. Now, what is the value of beta? Okay. We know that from the boundary condition that at r star is equal to 0, okay, df by dr star is equal to 0, the symmetry condition. Okay. Recall that f was equal to a sine of beta r by r plus b cos of beta r by r. Okay. The second term here goes to infinity, okay, as r goes to 0, which means that this coefficient has to be 0, okay, for a finite solution at r is equal to 0. Okay. At r is equal to 0, you can differentiate the second term, okay, and you will find that the derivative is actually 0. Okay. So, if you take the derivative of sin beta r, you will get cos beta r. Okay. Derivative of this thing is 1 over r is 1. Okay. So, I can expand sin of beta r is equal to beta r minus beta r whole cube by 3 factorial, and I divide by beta r. Okay. So, you can see that this function actually satisfies the boundary condition that the flux is, that the derivative is 0 at the origin. Okay. Or alternatively, the total heat transfer rate, okay, the total heat transfer rate has to be equal to 0 at the origin. QR has to be equal to 0 at R star is equal to 0, because there is no source or sink over there, and QR is equal to 4 pi R star square, okay, into the flux. Okay. It is equal to 4 pi R star square into partial T by partial r. I should have a negative sign there. Okay. So, this thing has to be equal to 0. The total heat transfer rate has to be equal to 0 as you go towards the origin. Okay. I made a mistake in the original formulation. R square times dt by dr has to be equal to 0, okay, as you go towards the origin, because you require that the flux has to be equal to 0. Okay, the total heat transfer rate has to be 0. The surface area goes to 0, okay, and therefore, the surface area times the flux has to decrease to 0 as you go towards the origin. Okay. And this one satisfies that condition. Okay. This first term here satisfies that condition, that r square times dt by dr has to be equal to 0 as you go to the origin, and t is finite, okay, as you go to the origin. Okay. So, I should change my condition there. This. Okay. This comes from the physical requirement that the flux has to times the surface area has to decrease to 0. There is no heat source there. Okay. So, the flux times the surface area has to decrease to 0. Okay. It does not mean that the flux has to decrease to 0. Okay. So, kindly note that correction. Okay. The temperature is finite at the origin, okay, in this case, because as r goes to 0, beta r also goes to 0. Okay. So, the requirement that the temperature has to be finite at the origin implies that f is equal to a sin beta r by r. Okay. You have the second condition at r star is equal to 1, okay, T star is equal to 0. What this implies is that beta is equal to I times pi. Okay. Okay, where I is an integer. Okay, because at r star is equal to 1, f is equal to a sine of beta. Okay. And sine function is 0 only at pi, 2 pi, 3 pi, etc. Okay. The sine function is 0 only at pi, 2 pi, 3 pi, etc. Therefore, sine of beta is 0 implies that beta is equal to I times pi, where I is an integer. Okay. So, that the sine function is equal to 0. Okay. Therefore, finally, we get for f of r is equal to a sine of I pi r by r star. Okay. And recall that g was equal to e power minus beta square t. Therefore, g is equal to e power minus I pi the whole square t. Okay. And therefore, the solution for the temperature is equal to a sine of I pi r by r times e power minus I pi the whole square t. Okay. This is a solution for any value of I. Okay, this is a solution for any value of I. Therefore, the most general solution is the summation I is equal to 1 to infinity A I times this. Okay. That is the most general solution, because this solution satisfies the boundary conditions for any value of I. It satisfies the differential equation for any value of I. Therefore, the most general solution is the summation of these solutions for different values of I. That is the solution for the temperature field, where the coefficients A I now have to be calculated from the condition that, from the initial condition that at T star is equal to 0, T star is equal to 1 for R less than 1. Initially, the sphere is at a higher temperature. Okay. So, therefore, this summation I is equal to 1 to infinity A I sine of I by R star is equal to 1. Okay. That is the initial condition. Okay. At T star is equal to 0, these exponentials are all equal to 1. Okay. So, A I sine I by R is equal to 1. How do we solve this? We have to use the orthogonality relation. Okay. So, the orthogonality relation in this case has a slightly different form. Okay. Note that these are the functions, these are the basis functions. Okay. These are the basis functions in which I am expanding the temperature field. Okay. The orthogonality relation in this case is 0 to 1, okay, R star square dr star. Okay. R square has to be used here because it is a spherical coordinate system. In a cylindrical coordinate system, we had used R dr. In a Cartesian coordinate system, it was dz. Spherical coordinate system, surface area is proportional to R square. Therefore, we have to use R square dr, okay, times sine of I by R sine, okay, divided by R, sine of j by R divided by R. Okay. And you can see this R square cancels out, and you get the same result that I had for the Cartesian coordinate system. Okay. You get the same result that I had for the Cartesian coordinate system, which was equal to delta I j by 2, okay, which was delta I j by 2. Okay. You get the same result as you get for a Cartesian coordinate system, because the basis functions are sine I by R and I am integrating over R square dr. Okay. So, therefore, I have to use this R square dr as the integral over of R square dr times 2 functions as the inner product in this particular case. Okay. Okay. It contains a factor of R square, because in a spherical coordinate system the surface area is proportional to R square, or the volume is proportional to R square dr. Okay. The differential volume is proportional to R square dr. Okay. So, in this case the left side becomes identical to what we got for a Cartesian coordinate system. We had already solved that, I will not go into that detail. Okay. So, what I have to do in this equation is to multiply the left and the right sides by sine j by R and integrate from 0 to 1 R square dr times the function times sine of j by R by R. Okay. So, this is equal to sigma I is equal to 1 to infinity. The integral in this case just becomes A I delta I j by 2 has to be equal to integral 0 to 1 R square dr, okay, times sine of j by R by R. Okay, on the right side multiplied by 1, of course, because the right side is just equal to 1. And the left side multiply this term here by sine j by R multiply by R square and integrate, you get A times delta I j by 2, okay, as I had shown over here, okay, by relating this to what we got in a Cartesian coordinate system. Okay. So, let us solve this right side first. So, this is integral 0 to 1. this r square will cancel out with this 1 over r, okay, and I will get dr times r sine of j pi r. You can do it by integration by parts. Okay. I write this as u v between 0 to 1 minus v du. Where u is equal to r, du is equal to 1, dv is equal to sine j pi r times, okay, v is equal to the integral of this. The integral of this is minus cos of j pi r by j pi. Okay, integral of u dv, okay, on the left side you have the integral of u times dv, okay, is equal to uv minus the integral of v times du. Okay. So, this uv is equal to minus r cos j pi r by j pi at the limits 0 and 1, okay, minus integral 0 to 1, okay, of dr, okay, v times du, okay. Du is 1 and v is sorry, du is dr, okay. Du is dr and v is minus cos of j pi r by j pi. Now, this term, okay, the first term at the upper limit it is minus cos of j pi by j pi. Okay. At the upper limit at r star is equal to 1, this is equal to cos j pi by j pi. At r star is equal to 0, this term is 0. Okay. At r star is equal to 1, it is cos of j pi by j pi. At r star is equal to 0, it is equal to 0. And then I have the second term here, which is minus sine of j pi r. Okay. Okay. There should be actually a positive sign here. Okay. Integral of minus cos is minus sine. Okay. There is a positive sign here, and this has to be between 0 and 1. Okay. So, here clearly the second term on the right, okay, for j being an integer, the second term is 0. So, sin pi is equal to 0, sin 2 pi is equal to 0, etc. at the upper limit. At the lower limit it is 0. Okay. So, this term is identically equal to 0, okay, and this term is minus cos j pi by j pi. Okay. Cos of pi is equal to minus 1, cos of 2 pi is equal to 0, okay. Cos of 3 pi is equal to minus 1. Okay. So, for all odd values, okay, cos is minus 1, for all even values it is equal to plus 1. Okay. Cos of 0 is 0, okay. J is equal to 0, cos of 0 is equal to 0, cos pi is equal to, I am sorry, cos of 0 is equal to 1. Okay. So, cos of j pi is equal to 1 for even j. Okay. Even j, cos of 0 is 1, cos of 2 pi is 1, cos of 4 pi is 1, and so on. Okay. And this is equal to minus 1 for odd j. Okay. So, cos pi is minus 1, cos 3 pi is minus 1, etc. So, I can write this as minus 1 for j, which is minus 1 for odd j and plus 1 for even j. Okay. So, this is minus of minus 1 for j by j pi, okay, which is effectively minus 1 per j minus 1, okay, by j pi. So, therefore, in this equation I have on the left side summation I is equal to 1 to infinity a I delta I j by 2 is equal to minus 1 power j minus 1 by j pi. Okay. This thing is just equal to a j by 2, okay, because delta I j is 0 if I is not equal to j. This becomes minus 1 power j minus 1 by j pi, which implies that a j is equal to 2 into minus 1 power j minus 1 by j pi. So, finally, temperature T star is equal to sigma sine of that is the final solution for the temperature field for unsteady conduction from a sphere. Okay. And once again, in this case as well, you can get numerical approximations. Okay. You can get numerical approximations for the temperature. Okay. This is the r star coordinate, r star is equal to 1. This is T star, okay. T star is equal to 1. Okay. At initial time, temperature is 1 throughout the domain, okay, and it decreases to 0 at the surface. Okay. It decreases to 0 at the surface. Okay. For T star is equal to 1, the temperature is virtually equal to 0 throughout. Okay. This is for T star is equal to 1. Okay. For T star is equal to 0.3, you get a solution that looks like this. Okay. And this series, okay, you can also consider the one term approximation. Okay, summation I is equal to or this is just equal to T star is equal to 2 by I pi sine I pi r by r e power minus I pi the whole square t. Okay, that is a one term approximation, and the three term approximation T star is equal to 2 summation I is equal to 1 to 3. So, by the time T star has become equal to 1, all of the approximations converge to the same thing. Okay. At T star is equal to 0.3, okay. Okay. You find that the solutions are all the same again. Okay. Even the one term approximation captures the solution quantitatively for T star is equal to 0.3. Okay. For T star is equal to 0.1, right, the exact solution looks something like this. Okay. The three term approximation gets it correct. Okay. The one term approximation is slightly higher. Okay. Okay, the one term approximation is slightly higher. Okay. By the time T star becomes, so this is that T star is equal to 0.1. Okay. By the time T star becomes equal to 0.03, okay, the temperature is pretty close, okay, to the initial temperature. Okay. Okay. And in this case, the three term approximation still gets the temperature reasonably accurate. Whereas the single term approximation is quantitatively different. Okay. The single term approximation actually gives you something that goes like this. Okay. And at T star is equal, so this is at T star is equal to 0.03. and at very early times at T star is equal to 0.01 the temperature looks something like this. Okay. It is close to a step function, and the 3-term approximation has spurious oscillations, okay, and the single term approximation gets it quantitatively wrong. So, these are the comparison of the numerical solutions and the actual solutions. At very early times, once again you can, if the penetration depth is small compared to the radius of the sphere, you can use an approximation where the similarity solution can be used if the penetration depth square root of alpha t is much smaller than the radius of the sphere. So, in that case you can use the similarity variable, and for t star is equal to 0.01 the similarity solution is quite accurate. Greater than that it is not quite accurate. Okay. And the similarity solution is valid so long as the thickness is small compared to the radius, so that you can consider it to be conduction into an from an infinite plane surface. If the thickness is small compared to the radius, it effectively looks like conduction from a plane surface, okay, and in that case you can use the similarity solution. So, this completes our discussion of unidirectional transport. Okay. We had looked at similarity solutions, separation of variables for unsteady cases, as well as steady solutions, okay, in Cartesian coordinate systems, in cylindrical coordinate systems, in spherical coordinate systems. So, next class I will start pressure driven flows. There is no equivalent of pressure for heat and mass transfer, it is present only for momentum transfer. So, next class pressure driven flows, first we will start with with potential flows and then go on to looking at viscous flows. I will continue this in the next lecture. I will see you then.